All right.
I'm delighted to be here today with Dr. Delbert Larson, who has a PhD in physics and decades of experience as an author and reviewer of peer-reviewed scientific works. He's had positions at well-known institutions such as the Superconducting Super Collider, where he had a leading role on longitudinal physics design. And he also designed and led the construction of two working accelerators, one of which employed relativistic particle velocities. I got interested in Dr. Larson because of his Twitter feed, where he talks quite a bit about a new theory that he has about the ether. And this is something that's been a matter of curiosity for me for some time. So I wanted Dr. Larson to come on and talk about his theory. And I wonder if you could start by telling us a little bit about your background, how you got interested in this, what from your childhood or your early years led you to pursue physics in the first place, and then maybe we can get started with basics of the theory.
All right. The original reason for me to go into physics was that I was told in the 70s that mankind was going to run out of oil, which would be a complete disaster. And so one of the motivating goals was to look into whether I could contribute to a fusion energy system to bring to mankind. And that was one of the prime drivers early on. And then when I got into graduate school and even the late undergraduate days, things started to get a little bit detached, in my view, from a physical reality. And that formed some of my thinking going through those years, although I came to the realization that what is presently called physics is largely, in my view, just a mathematical enterprise. And I shouldn't say just, I mean, mathematics is clearly a very important thing, but it's just in the sense that there could be math linked to the physics. And right at the moment, it's pretty much just the math. But one can do an awful lot with that math, and it can be very, very powerful. And in my graduate days, I did design a 3 million volt electron accelerator system. We had a terminal shell that was at 3 million volts, surrounded by sulfur hexafluoride so that it doesn't arc too often to ground. And then that formed an electron beam. And then I designed the electron optics using the equations of the time, which were the Lorentz force equation and Maxwell's equations, and they are known to be relativistically sound, and we used relativity in that design. And then from there, I had a couple of other jobs that led me eventually to the superconducting super collider, where I did design of the longitudinal portion of that machine. I wrote a computer program there. Unfortunately, that project got canceled, and it was rather a significant blow to my career because there weren't as many jobs for accelerator physics people once that went away. I did manage to get on a project at Fermilab, and that was the second accelerator that I designed, and it worked properly. And it was I designed a medium energy beam transport system that operated at 1 million electron volts, which was a non-relativistic beam. But I developed all of the equations to do that analysis. That then tied into what I wanted to do for fusion, because the beam energies and species were fairly similar. And so then I spent 6 years on my own working out a fusion design. I had run into a situation where I found that physics careers generally are directed. If you've got something that's considerably off the mainstream, it's very difficult to work on within the way things are set up. So I turned to IT to generate my income, and I worked on that project then. I tried to find some funding for it for 5 years. And when that didn't come, I had some other theoretical pursuits that I wanted to follow up on. And that led me to the ethereal work, which ties all the way back to those early graduate school days, as my guiding principle has been to try to go back to physics as the foundation. And by that, I mean an underlying assumption of an objective reality that one then hypothesizes about. and you set up your hypotheses based on that, and then logically develop those hypotheses to arrive at the equations that you then test. And that then led me to work on an ethereal alternative to relativity.
One of the things you just brought up struck me as kind of connected to an idea I've been mulling over lately, that maybe mathematics, rather than being suitable as a foundation for physics, is actually just the limit. In other words, you use the objective reality of physical laws and everything to work things out, but then when you hit a limit in mathematics, you realize you've gone too far. Where nowadays it seems like a lot of physicists are using mathematics to get to some beautiful theory that works in the math, but it doesn't work in the real world. Does that make any sense?
Somewhat, I would give somewhat of an agreement to that. I certainly agree that the math is built into these beautiful theories, and then what tends to happen is um, there may be found some exceptions to what is presently being modeled. One of the present things that I also believe is a bit of a problem is the existing Lagrangian for the standard model in physics has over 150 terms and 19 free parameters. And it is difficult to continually add things to it. So they are certainly dealing with constraints. But I don't, but a lot of times you can, if you're clever enough, figure out how to squeeze the new result into it. And that's when we kind of depart from it being a theory that's, I would say, sound, because if you can always model the data by addition, then you don't really have a good feeling that maybe everything is certainly not as simple as it I would think probably is. Although I have to admit that that's a prejudice. I think things should be far simpler at a physical level than the present mathematical details. I
So
don't know. Does that
why do
answer
you
your
say that's a
question?
prejudice?
What's that?
Why do you say that's a prejudice? You have a prejudice towards simplicity. That's
Yeah,
what.
well, there's no particular reason why the world would have to be simple. But it could be, and I think it is. But that is a prejudice because it might be very complex. And if it is, maybe the present theory is as good as we're going to get. I just don't think so.
So so in moving ahead on your theory, I picked up so many things from your Twitter feed, and I have also tried to spend some time with the material you put online of your you have a website called larsonism.com, if anybody wants to check it out, that has all of your material written out. And now I seem to have lost the main document from your website, but anyway, I've got the notes. You said that your theory meets the classic tests of general relativity, and then you list 5 classic tests of general relativity. And I wonder if you could just walk through that with us a little bit and explain why it's important that a theory meets those tests.
Okay. Since I don't have my notes in front of me,
Well, I'll read them for you. The 5.
okay,
Yeah.
that
Okay.
would be great.
Okay.
And I can go through one at a time. I just might forget one at
Yeah.
any moment.
Well, there's one I'm mainly interested in, so I'll read through all 5 of them, and I'll go back to the one that I thought we could talk about the most, because there's only 2 of them that I even have a grasp on what you're talking about.
Okay.
So the theory is shown to successfully meet the classic tests of general relativity. Calculations for the advance of the perihelia, the Shapiro effect, the gravitational redshift, the experimental result concerning the bending of light in gravitational fields, and also gravitational waves are understood in a theory. And the first of the field masses allows for an understanding of what is presently known as dark matter. So I guess I'm most interested in the 2 that are relative to the gravitational redshift and the dark matter.
Okay. Well, the reason it's important that the theory agrees with relativity, for the most part at least, is that there's a considerable amount of data on all of those things, except for dark matter. The other ones that you mentioned, those all have been tested fairly well, and they agree with general relativity's equations quite well. And so now the theory that I've developed does have a slight difference from what I've calculated so far with regard to the advance of the perihelia, but it's not large enough to necessarily detect right now. And so I think both theories are consistent with the data. There's a lot of trans-Neptunian objects floating around in the solar system, and moons and planets, and that we don't know the masses exactly on. And so there's a theoretical and an experimental uncertainty, and both theories fall within what we observe. As far as the gravitational redshift, uh, in the theory that I put forth, it's simply gravitational. If you assign a photon a mass given by its energy divided by c squared, and that's a mathematical reorganization of the E equals mc squared formula. If you give it that mass, E divided by c squared, and then assume that it is attracted to the star by the normal gravitational attraction, as it leaves the star, it will lose some energy because of that, because it's fighting its way out of a potential well. And that then leads to a redshift. So that's the gravitational redshift one. And then in the theory I've come up with, I identify two field masses. There's a series of forces that exist in the ether, and there aren't that many. I basically start with an ethereal cube that has an internal tension, and then it's quantized. And since it's quantized, you're going to have quantum energies. And if you make a cube smaller, the quantum energy will go up. So what that essentially does is it leads to a repulsive quantum force that you can envision at the edge of the cube. So you've got the quantum force pushing outward and the tension force pulling inward, and that's how you get an equilibrium size for the ethereal quantum. Now, as you move a quantum through the quantum and tension fields, then they will change those fields. So that will then lead to field differentials as you go through space, based on where you may have charges or mass. And those fields then are going to have energy. And that energy then, again, if you take energy divided by c squared, you're going to get a mass. So those fields are going to have a mass density throughout all of space. And there were two components that popped right out, one of which was positive and one of which was negative. The negative one was the one that led to, or leads to, the advance of the perihelia, and the positive one is the one that leads to dark matter. And the dark matter that you get out of it, if you've got a very large mass concentration at, say, the center of a galaxy that may have an extremely massive object there, maps pretty much exactly what you need to describe the observed dark matter in galaxies. So it comes out straightforwardly from that positive mass field effect. And I guess at this point it might be good to note what the advance of the perihelia is.
Sure, but
Um,
does that imply then that there's no need for these dark matter calculations that are currently being used in physics to explain the gravitational problem?
well, yeah, this is a this should solve that problem. And not only that, but it should be calculable. Because the other thing was that uh, a very large mass like you have in the middle of the galaxy will push out one of the ether components and pull in the other one. And that's what leads to that the dark matter, the field mass. But if you've got another galaxy somewhere not too far away, say in our case Andromeda, it's going to pull one out and push the other one in. And halfway in between, or actually at the center of mass between the two galaxies, those effects are going to cancel. And so there won't be any field mass in between the two galaxies at that point. So you can use the theory that I've come up with to calculate where this field mass for the most part will be. Now, one thing that you cannot do is you cannot necessarily rule out the fact that there may be what are presently called black holes, but let's just call them neutron stars because my theory does not have a singularity either. And if you've got neutron stars in various locations, they're going to set up gravitational fields and they're going to be pushing and pulling on the ether, and they're going to set up some dark matter as well. So it's not completely obvious how you find that because uh, they they're dark, so you can't see them. So that's kind of that's how you would go about trying to calculate the dark matter in this theory. However, you start with what you do know. I mean, you know where the supermassive central objects are, Sagittarius A star in our galaxy. You know about what its mass is, so you can calculate the pushes and pulls on the ether, and you can get the first order cut on what the local dark matter would be. And then if your calculations start to show up that you've got something that kind of looks like, well, maybe there's another source here, that may come from other objects that we can't quite see. But it's a lot different than what they're looking for now with these WIMPs, the weak interacting massive particles and all the other stuff that, that the physics Inc. is looking for and has not yet found.
Okay, so I derailed you for a second there. You were going to tell us about the advance of the perihelion.
Yeah, that was the first thing that really Einstein solved, and that was a very monumental achievement on his behalf. The orbit of the planet Mercury is elliptical, and the axis of its ellipse uh, processes some over time. And it was calculated very well by people back in the late 1800s, early 1900s, but there was an anomaly that could not be understood. And that was the contribution that general relativity gave, was it offered a very good explanation of where that came from. And all of the planets have this. And in my work, I've got a table, and it shows what general relativity's calculation is versus the one that I put forward based on that negative field mass effect that came out from this pushing and pulling of the background ether.
Okay, well, with that background of why you felt that those were the necessary things that would that your theory would have to account for, then could you give us a little kind of summary of the theory, and then we can start talking about aspects of it?
Yeah, sure. It's probably best to start with the earlier ether theory.
Okay.
There was a theory that predated relativity back in the late 1800s, and I think it was maybe mid 1800s. I'm not fully a historian of the matter, but right up until the early 1900s, there was a theory of the of the luminiferous ether. That theory came about because light has wave phenomena. It's known that light is transversely polarized, and what that means is that the motion of the wave is perpendicular to the direction that the wave is going. And it's known that that sort of behavior also happens in solids. One solid, for instance, would be a wave on a string. If you crack a whip, the pulse along the whip goes in a direction that's perpendicular to the length of the whip, but the pulse itself goes along the whip. So there you have a transversely polarized wave on a solid. And so it was thought back in those days that since light was a transversely polarized wave, it was likely a wave on an underlying solid substance, and that substance was called the ether. And it was very strongly believed in because it made a lot of sense that this ether would exist throughout all of space. That's why the starlight still gets to us, is because it's oscillating on a background solid. And that, so that's where we were at that time. And but the next thing to try to do was to try to determine, well, is the Earth moving through that ether? And to try to find that, there was an experiment that's quite well known called the Michelson-Morley experiment that set up two arms of a mirror going perpendicular to each other. The one that's going up and down is going to have one path, and then the light's going to go on the other path in the other direction. And if you look at this from the point of view of the ether, the Earth should be going through it fairly quickly. So this is going to go past you. That means that the one path is going to go up as a triangle and go down, and the other path is going to go forward and then come back, and then they're going to meet again. And if you calculate and do the math, you see that the trajectory going in the forward and back path is a bit longer than the one that takes the triangle path. And so if you then rotate this so that they get they exchange places, then their roles are going to be reversed, and any time difference should show up, because when you look through the apparatus, you could see fringes of where the light was interfering. And when they did the experiment, there was none. And so the conclusion had to be, well, something was happening. And the thing that was proposed, one thing that could be proposed is either the light is dragged along with us, or another thing is we could be the center of the universe, but nobody really believes that because the Earth's is orbiting around the sun. So what eventually came about was a proposal that the length of the device moving in this direction that it took longer shrunk a little bit. Because if you do that, then you get a zero result. Then the timing is the same in both directions, and everything works out with regards to what the experiment is telling us. So that was fine, but then additional experiments came around, and it found out that as clocks went through this ether, they also slowed down. And they slowed down by the same factor that the length was shrinking. And that had the rather odd effect that if you were to set up a coordinate system with your faulty clocks and your shrunken sticks, that you would measure the speed of light to be the same as you did if you were at rest at the ether where the clocks and sticks were correct. So Einstein took that result, and he ran the calculation backwards and ended up deriving the same equations that related space and time with these length contraction and time dilation effects. And that became special relativity. And Einstein's theory was much more elegant than the other theory, because the shrinking of the device as it moved through the ether and the slowing of the clocks as they moved through the ether were both considered, and they were, ad hoc proposals. It was just thrown in. And so Einstein started with a different proposal, that the speed of light was constant and that nature's laws should be the same whether you're moving or not. So that's the difference between the two in that regard. But the additional difference is the whole concept of space and time itself, because in the old ether theory, space was what you generally would think of it to be when perhaps you first think about what it may be. There's going to be a direction that way that goes on forever. It's going to be one that goes up forever and then sideways. So you've got three spatial dimensions that just go on. And time is what we measure on a clock. It has a before and an after, and you can watch the hands of the clock tell you how much it advanced. They were completely separate concepts, but if you have relativity, you start to mix the two. And so if you have a finite length in one for one observer, and then someone's moving, it becomes both a length and a time. And so that was a very bizarre uh, path to take. And I remember asking my professors many years ago, well, why did we take that step? Why didn't we just stick with the old idea, which was given by Lorentz? And the answer was that Lorentz was shouted down. So 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 that's where we are on the special relativity. But the big thing that Einstein brought that was different because the Lorentz had this ether theory with these length contractions and time dilations, and it gave identical math to special relativity. So it was just a matter of picking one or the other. But when Einstein came up with the curved manifold space-time continuum idea, and he also showed that his equations gave the proper advance of Mercury's perihelion, and further that he predicted a bending of light that came out to be correct. It all got in the newspapers, and his theory was adopted at that time, and reasonably so. The only thing that's always quite nagging about it is it's very difficult to understand conceptually what it means for space to become time and time to become space and how these things could possibly be curved on a manifold. It's a very kind of bizarre concept, but it does work, and so it's celebrated. So then, but I always had a deep problem with relativity early on because it just went back to some very simple experiments. There's an experiment called the two-slit experiment where light goes through two slits and it interferes on a wall behind it.
Mhm.
And in relativity, it was very hard for me to understand how that light could hit the wall the way it does. Quantum mechanics tells us that there's an entity called a wave function, which is presently viewed as a probabilistic distribution that tells you where an underlying particle may be. So if you have this wave function go through two slits that are separated by a significant distance and then travels to the wall, the wave function will interfere with itself to give you the pattern that we see. But the question is, if one part of it on the far end of it hits the wall, then that entire wave function has to collapse at that point. But how does the other end know that that happened? And under relativity, it gets worse because if you go on a rocket ship parallel to that wall, what is called simultaneous changes. So it doesn't make sense how that can happen. And then later there was another experimental group of tests called entangled states that also show a phenomenon that can best be described, in my view, by something happening in a faster than light way.
Mhm.
And that then requires us to consider setting relativity aside. Now we can go back to the special the ethereal theory from before fairly straightforwardly, and we can again embrace the physical length contraction and a physical time dilation in a stationary ether. And that gets us again right back to being identical with special relativity. However, there's a big hurdle left, which was to replicate everything that general relativity does for us with regard to the four classic tests and other other ramifications. This whole idea of having a black hole in space, you need another model for what those large objects are. So originally, I had just set my sights first on working out Maxwell's equations, because Maxwell himself had spent a good part of his later years trying to derive his equations from some sort of a mechanical model, and he had not done so. And there was an effort right up until relativity got embraced to to do that modeling. And back at the last year of the SSC, when it was dead and none of us had jobs, I worked out a two-component ether model that derived Maxwell's equations. But I knew at that time that there should be more to it, because if Maxwell's equations result from this two-component ether, and if electric charge is essentially ether that's been detached or kicked out of the underlying solids, which is what the model shows, then the Lorentz force equation should also be able to be derived from the same ethereal tenets. And so that was my first task. And that took quite a while, but I did come up with a series of postulates that leads to both. And then I thought, well, why don't you take a look at gravity? That wasn't my original goal, but I plugged in an effect that said, well, if mass will reduce the tension field and also reduce the quantum force on these little cubes, but do so in a way that's not equal, what do you get? And I got Newtonian gravity, and I got the right equation for the advance of the perihelia. And that, well, this is probably heading in the right direction. Now,
So
it took a
I just
long
I gotta
time
stop you
to
here
get
for a
there.
second. What gave you the thought of looking at it in a way that is not equal?
Oh, because I knew what the
I mean
answer had to be.
that's got to be some kind of insight. That I mean, that's amazing.
Well, I knew where it had to go, and if they were equal, you weren't going to get an effect. And so it had, at first, I think I played, and most of the time when I developed this took 6 years. And I would be thinking about individual pieces all the time. And I've had, I think it was 42 versions of the originally entitled LFE, which was Lorentz force equation paper. And then I think it was another 8 when I had 8 versions of the paper that got into this. And I would just come up with all kinds of different ideas as to what might be causing it. So the one that stuck, that worked, was the one where they weren't the same. And not only are they not the same, but the positive ether has the opposite characteristic as the negative one. And that's what made everything work.
Well, so when you looked at it as in a way that's not equal, you said then out of that fell all these equations. What were which ones again fell out of that?
Well, Newtonian gravity,
Okay.
and then the advance of the perihelia came out as well. And that was very early on. But then of course, as the story goes, I had a sign error. And it took me a long time to run that down, because there's two additional fields in the ether besides the tension and quantum force and quantum fields. There's a delta field that comes in, and that's when you've got a free piece of ether that pushes the positive out and the negative in, if its self is a positive charge. And then there's a gamma field that uh, that is caused by the motion of that's seated by mass. And the thing that finally allowed me to get rid of the sign error in the gravitational piece was that the gamma field had two components, which I didn't for a year, I spent trying to figure out where my sign error was. And then because the math is kind of long and sign errors are tough to run down sometimes. And it wasn't there. And so when I realized it had two components, it also made sense that it would have two components because energy makes mass makes is an input to the quantum energy of a cubic square well. And also, if you heat up a spring, it gets softer. So it makes some sense that the energy that is mass, if you put it into the ethereal quantum, you're going to get these two effects. And it was at that point that everything came together and all of the pieces worked.
So it was actually a serendipity that you had the sign error.
Well, it was yes, because I might have just given up. Well, I don't know that I would have given up because you keep tugging at this, at the string. But the fact that I calculated the perihelion, it came out right. I was it was one of those. It's one of those things. I mean, right out of the box, it was it was within a few percent. And I of course thought, well, okay, I must have an error somewhere in what I'm doing because the calculation of it is pretty. One of the rather funnier stories is that the calculation of the advance of Mercury's perihelion perihelion takes took me longer to calculate on a computer running in my office because I'm running on a PC. And it took longer to calculate that than it took Mercury to actually go around and advance the perihelion. So the equation got kind of tough after a while. So it didn't come out to that accuracy right away, but I was on the right track. Yeah. And the minus sign, I mean, it was just there. But yeah, the fact that I made a mistake made me a lot more optimistic. And then I got down and then right, that's how it went.
So I'm curious about this thing with the measurement stick and the clock. Um, you say to go back to the original theory, the measurement stick actually reduces in length, and the clock actually slows down. That's in physical reality.
That's well, okay. There is some if you take the ethereal standpoint, that's correct. If you take the relativistic standpoint, then it's all relative. That's
Right,
the difference
right.
between the two.
But with the ethereal standpoint, so is that because of some sort of compression that takes place when the stick is moving against the ether?
I haven't, well, Lorentz had a theory he called it the theory of electrons, and he had a theory as to why that occurred. On my work, I haven't asked that question. I've just accepted that those two things happen, and then we move on from there. And that's a good question. We should always ask why, but that one I have not gotten into.
Is that essential for the theory though, for the new theory to move forward? Is that assumption essential?
Yes.
Okay. Okay.
Why it occurs is not, but the fact that it does occur, yes.
Okay. So as I was looking through your theory, there's a few things that's jumped out at me. You said that the ether, in the ether theory, it says that when you move, your clocks and your meter sticks become faulty. But when you're at
Yes.
rest, they don't, obviously. So, um, so that seems to bring up to me something about the whole measurement problem in physics in general. Um, and that was certainly a problem with the Michelson-Morley experiment, right? Because the part, I think what you're saying is that part of the reason that they couldn't detect the ether was that they didn't recognize that there was this fault in the, or did they recognize that there was actually this physical shortening and then it was just the people who came after them that wouldn't recognize it?
Yeah, well, prior to doing the test, it wasn't believed it was there. Once the test was done, it was a theory as to why the null result occurred. In recent years, it's very difficult to get it through people that the Michelson-Morley experiment did not disprove the ether. All it did was it disproved that it proved that there must be a length contraction of the apparatus. And it's important to note that relativity has that same length contraction. So the special relativity theory and the ethereal theory are identical mathematically at that level.
Okay. Wow. Okay. So in relativity, then it says that all time and space measurements are equally valid. But in ether theory, it says only those at rest with the ether are correct. Only
Correct.
those measurements that are at rest with the ether are correct. Is that in general, or is that just when in something like the Michelson-Morley experiment?
It's generally true.
So
And
what
there's a bit of a
these
caveat there. There's a bit of a caveat there that, and I don't know how it might be more confusing than educational, but the length and the time have to be correct somewhere. It wouldn't have to be at rest with respect to the ether, but it's the most likely scenario.
so they have to be correct somewhere. You mean that
In the
there
ether.
has to be a valid, there has to be a valid representation of them in order for them to have become shorter. I think this goes back to your one of your basic assumptions is that there is an objective reality. That's a very
That's part
important
of it.
part of your method, right? Of
Yes.
your theory. There actually is an objective reality. And in a little way, you're kind of fighting upstream with a lot of physics on that one.
That is correct.
So, well, we can talk about that later, the fighting upstream with physics. So you talk about, rather than space-time being like a manifold in relativity, you talk about space as being the stage upon which events occur and time as providing the ordering of events. And so you're kind of midway between the general world of physics and Stephen Wolfram. Have you run into Wolfram's theory of his new theory of fundamental physics?
I looked it over some and it did not resonate with me. And so I haven't studied it in great detail.
Uh-huh.
I,
Well,
I saw a
his
few things
idea
I've
is that time is the updating of events. So there's some sort of energy falls out of time because time is the updating of events.
that's
But
where I would not agree. Yeah, to me, energy is constant. There's conservation of energy.
when you say constant, do you mean continuous rather than
I mean,
discrete?
there's a conservation of energy. So time is not going to drain energy out of anything.
Oh, no, he's not saying that time drains energy. He's saying
Oh,
that time, um, it's very complicated because this causal flux of edges of space is what is energy is the causal flux of edges of space as time is updating the events. But space, he says that space is made up of that space is not just a stage upon which events occur, but space actually is everything. And it's made up of very, very, very tiny particles, far tinier than the standard model, made up of these probably smaller than the Planck scale particles that he calls EAMs. And those EAMs, it's the way that they connect with other EAMs. It's the relationship between where the EAMs are. It's all these edges. And that's the way the universe kind of builds out, so that space itself is made up of these particles. And then time is the updating of events. So anyway, if you haven't looked at it, it's kind of irrelevant to the conversation, but it just felt like your concept here is kind of midway between standard physics and Wolfram's idea. So I thought it was kind of interesting.
well, and you raise a good point too, and that is that in in my way of thinking, space and time are are just they're conceptual entities that don't themselves have any structure. it's the ether within space that is providing the physics. Where it sounds like in his theory, he's ascribing um, a mechanistic or physical model to space itself. And that would be a departure between what he's doing and what I'm doing. And also a bit with regard to the relativistic view of it being a manifold that, sloshes around from time to space and that sort of thing.
Well, so you're talking about ether as filling all of space, and ether itself is made up of some sort
Quantum.
of, well, you said that normal matter is positive nuclei and negative electrons, and solid ether or solid matter is it ether a matter? A kind of
I,
matter?
I'm not entirely sure what all of the interior properties of ether are.
Okay.
When I was working through it, I there was a model I really liked, which was that it's positronium, that it's an atom of an electron um, interacting with a positron, and basically you'd have an infinite electron sea and an infinite positron sea. And the reason I liked that model originally was it's the ethereal theory is quite clear that free ether is charge. And if you put enough energy into what's considered the vacuum, which in this case should be putting it into the solid ether, you can knock out a pair of charges. You can knock out a positron electron pair. And so that could maybe tell you that it that's what it's made of. And it would go back to the old idea that Dirac had about there being this infinite sea of electrons. But here we would add an infinite sea of positrons as well. And that's what the ether would be. However, the problem that one runs into is it's not obvious that that's the case, because I would think if it was made of positronium, then the individual quantum bit would be fairly large. And I have some difficulty then seeing how Maxwell's equations would be valid all the way down to the nuclear scale. And that then pushes you to a different model that it's got some positive charge and some negative charge constituents that are smaller than what you would think for positronium. And I have thought about what it could be, but at this point, it's an open question as to exactly what material it's made of. We do know that it's plus charge and minus charge, but what it's been, and we also know that it's fermionic, which means it has half integer spin, because the Pauli exclusion rule is what makes it such that one cube of ether cannot be when you try to push two or three cubes together, you can't get them into the same spot. And that's what leads to the quantum pressure. So there's some things that are known about it, but not everything is there yet. And I would love it if other people would dig in and contribute ideas.
Well, I have my own personal idea, which is very
Okay.
difficult to explain to anybody. Um, Obviously, you understand the difficulties of these things because you've worked for years and years on this thing, right?
Yeah.
Um, so I don't even know if my idea has anything whatever to do with physics, but I think it's something that's underneath the physics. I agree with you that the universe is very simple. I think it's very simple. I think it's actually probably simplifies back to there's the one, of course, but then there's also, I think marriage is very fundamental to the universe. And so when you talk about the positive and negative ether, it makes perfect sense because that's a kind of a marriage, in the same sense that the positive nuclei and the negative electrons are a marriage. in the same sense that the two hemispheres of our brain, the left and the right hemisphere, are a kind of a marriage, and they work in a kind of beneficial adversarial way against each other to produce, to create. And so it makes perfect sense to me that your ether theory would be correct based on this vision that I have of how the universe works through creativity. But I apologize for even bringing it up because I can't describe it very well. And every time I get started trying to describe it, I just end up in a tangle. So let's go back to ether. It makes more sense.
Well, there's a difference. There certainly is a difference in perspective, in my view, between what an artist does and what a mathematician's going to do with a basic physical model. And I would say that some of the themes that you touched upon do exist. The one thing that made me chuckle was proving objective reality beyond a shadow of a doubt, because I've had enough interactions with and there aren't even that many, but with philosophers, and nothing is beyond a shadow of a doubt. It's the arguments go on forever.
Well, okay, we won't say beyond a shadow of doubt, but he did.
Okay.
He has very compelling. Let's say very compelling.
I believe it. I mean, I that's my touchstone, is that there is an objective reality. I just know that trying to convince certain sectors of the intelligentsia of that statement is challenging. That's all I
Well,
can say.
his basic work came. He's known for a lot of things. The thing that's really current in everybody's interest right now is his theory of affordances. I don't know if you've heard of that at all.
That I haven't.
Um,
You'd have to, if you could
um,
send me a reference, I could look
well,
into it.
a very simple aspect of affordance would be, so I've got a cup, and when you look at the cup, even if I didn't, even if I looked at the cup without having any experience with the cup at all, this has got a handle. It would be obvious that I would go like this because it's sort of made for me. It fits me. So um, I see it as a tool or as a useful thing even before I see what it is. I see the usefulness of it, what it affords me. It affords me something that I can put liquid into and then drink out of it. Even if it weren't made by man, even if it was a gourd that came off a tree, I could look at that and think, oh, this would be useful for drinking out of. And that's the basic underlying idea of affordances. So that's one of his theories that became very popular in current thinking. But his theory of ecological perception comes out of his work with the Air Force during the war when they were trying to find pilots that could land on aircraft carriers. Well, maybe it was after the war. I can't remember when they had the aircraft carriers. I think they had it in the Second World War. Yeah. So the visual tests that they were running in the lab with these pilots to determine which ones were going to be good never helped them at all. So they'd pick out some pilot and they'd think, oh, he's going to be able to do it. And then he couldn't do it at all. He'd crash and burn. So Gibson said, you know, when you test these guys, you have to test them in a real world environment because perception has to do with the real world environment. So they started testing them based on that. And what he found through all of his investigations with these pilots is that what they were seeing and the way that they were gauging distances had to do with the way the light reflected off of what they were seeing. So there's actually something there. It wasn't just like not a flat digital image that I'm looking at. Like right now, I'm looking at you on a screen and there's a flat digital image there. And I could guess something about the distances based on my knowledge of bookshelves and how far your head would have to be in front of it. But basically, I'm just looking at a flat visual field. But
Mhm.
but in reality, there's an actual three-dimensional field there. And there's actually light bouncing off of the things that are in that field. And then they're seeing that light. So from that, and it's way more complicated than that. He has a lot of data on all this, but his basic work rejected the perspective that perception in and of itself is meaningless. And he argued that meaning is independent of the perceiver. The environment decides perception, and meaning is in what the environment affords to the observer. That stands out to me because I'm very fond of the work of Jordan Peterson. And Jordan Peterson has a very compelling argument that meaning precedes matter. And I think there's something to this whole theory of the ether that has something to do with meaning. Because especially when they talked about the luminiferous ether as being the ether is that which carries the light. It's such a beautiful image. It's almost poetic, right?
Yeah. No argument there.
Yeah. Well, so now we're up to the point where the ether is, you're using the term cubic square wells. Is that right?
Yes.
Describe these
Yes.
like
That's the simplistic model of the element of it. It's
so would you call that like you're thinking of it as a particle or some element that's in the, do you have a word for those cubes?
well, yeah, I mean, you can think of if you had a bunch of perfect little ice cubes, right? And you took them out of your freezer and you just stacked them. You put them a row of them on the floor, and then you put rows and rows and rows, and then you get layers and layers and layers. Each one of those individual cubes is a cube of the ice that you took out. The ether, and in the case of ice cubes, the same thing would happen over time. If you just let it sit and they got a little warm and then you froze them again, they'd be stuck together, and you'd have a lattice work of these cubes, and that's what the ether. That's a modeling of what the ether is. You're going to have neighboring cubes, and from the Pauli exclusion rule, they're not going to be able to squeeze together any tighter than a certain limit, and that's what forms the cubic square well boundary of the individual quantum. And then you can use very simple quantum mechanics, the quantum mechanics of the cubic square well, to analyze the energy and force on the cube faces from that setup.
So that you have an internal tension that's compressing the cube inward, and at the same time a quantum pressure that's pushing the cube outward.
That's correct.
And that's what's keeping the cube in a stable
Yeah,
size.
yes.
So
Yep,
it's always the
that's correct.
same size.
No,
No?
no, it would be if it weren't for other effects. So if you started with no mass and no energy in the entire universe, then that is what you would have. You'd have these individual cubes, they'd all be the same size. But if you put some energy into the ether and you knock one of those cubes out, you're going to knock both a positive one out and a negative one out. Now you've got a hole. Well, the whole thing's going to reshuffle back, and you might think that it would all be the same. But where that one was that you kicked out, it's going to push the ether of the same kind outward, and it's going to pull in some of the ether of the opposite kind. And so at that point, you start getting a distortion in the size due to the existence of extra ether that you kicked out. Also, when we mentioned earlier, what happens if you've got what I call extrinsic matter, protons or electrons or stars, and if you put that into the ether, that's the energy that alters the quantum and tension fields, and so then you also get a disturbance in the size of the individual quanta from those effects, and that's what leads to all of physics.
So it's the disequilibrium.
Well, no, it's still in equilibrium. It's just there's another player involved. And in fact, there's two different types. When you've got the extra ether, which turns out, as I mentioned earlier, to be charge, that's when you kick this extra piece out, and then it's going to push the like kind ether away some, and it's going to pull the unlike ether in. That leads to electromagnetism. Whereas when you've got mass, and that's another player, then it changes the uh, constants associated with the quantum and tension fields, and that brings in one type of ether and pushes the other ether away as well. So you've got they're basically different participants in what's going on, but that's all there is. There's no there's no other effect. So that's what makes it very simple. The underlying physical theory is extremely simple to get the very complicated equations of Maxwell, Lorentz, Newton, and dark matter, and uh, the tests of general relativity.
So, so both charge and mass are they're each keeping things moving based on this kicking out and pulling in, kicking out and pulling in.
Well, they don't move
Oh,
necessarily. They displace. They
displaced.
can move. Yeah, they can move, but you can think of it just as if this is the normal ether, and then I put a little bit of extra ether in, it's going to do this because it can the like kind will just expand, and then the unlike kind would contract. And what that will do is it will equalize the density of the positive and the negative ether, even though you've added some additional positive ether into that area. So that's what leads to what's called Poisson's equation for the electromagnetic portion. Well, the Poisson's equation, that's one of Maxwell's equations. So that's that effect. It's that simple, but it's a displacement. When you start getting into motion, if that charged, if that extra piece of ether starts moving around, then it's going to impart motion to the background ether as well, and that's what gets you to the rest of Maxwell's equations. And then on gravity, it's similar. The mass is going to do that same thing, moving things in and out. And then if the mass moves through it, you're going to get moving ether as a result of that. So it's both motion, but the predominant effect is a displacement. But then if that which is causing the displacement is moving, then its effects will move as well.
Well, the reason I'm getting particular about this is going back to Jordan Peterson's ideas, where he's talking about kind of the archetypal patterns of the world, kind of the basic patterns of the world. One of the things he talks about is you have order and then you have chaos, and there's a border between order and chaos. And order can be either a good thing, good quality, benevolent kind of order, or it can become tyrannical, become too tight, too rigid. And chaos can be completely so much chaos that it's unmanageable. Like, if you break your leg and at the same time your car breaks down and, everything goes wrong, or even just the kind of chaos where there's a tornado happening and you can't get into the basement or whatever, chaos, just in general chaos. And I'm sure there's some chaos in physics as well. But chaos can have both a benevolent side and a negative side. And the benevolent side is that usually, even when you're in chaos, there's some treasure there to be found, almost like your little, you had a sign problem. And because you had that sign problem, you went back and found something that you might not have found otherwise, or it might have taken you a lot longer to find it. So these little anomalies that happen that are like little treasures in the chaos. And so sometimes when order becomes too rigid, too hard, and then you either can move over into chaos voluntarily or accidentally. But when you're there, you can get something new that you can bring back into the order and help the order not to be too rigid. So then the order becomes benevolent again. And I almost get that picture when you're talking about your ether, some things will be displaced and something else will be brought in, but that's what's keeping the whole thing alive. That's what's causing all of these theories to be part of that. It's almost like that's almost like what's part of building everything is keeping that motion. Well, it's not motion, displacement. And so pushing out and pulling back in, that pushing out and pulling back in is keeping this thing going. And I think you have some interest in the Bible. Am I correct?
Yeah, I certainly. Well, I'm a religious man.
Yeah.
I'm a Christian.
Okay. Well, I am too. So lately I've been studying and studying and studying Genesis 1, chapter 9, Genesis chapter 1, verse 9, because it talks about the gathering of the waters. God gathers the waters so that the dry land may appear. And I looked at that word gather in the Hebrew because I thought this is such a strange word to use. He gathers the waters. It's almost like a relationship thing, like gathering us all together or something. He's gathering the waters. And the word gather there, it's translated gather everywhere else in the scriptures, that Hebrew word. But that Hebrew word actually has the meaning everywhere else that it's translated in the Bible. It is translated as the word wait or hope. But in that particular verse, it's translated gather because it would probably wouldn't make any sense to people if it said that God held the waters in waiting or hoping or something, like the waters were waiting and hoping while the dry land appeared. Because everywhere else it's translated wait, endure or wait. And so then I dug a little deeper into that word, and that Hebrew word actually also has a meaning of twisting or tension, the kind of tension that comes with long enduring, long waiting. And then it also gets down to this idea of a cord that's made up of many fibers or that's twisted. And I started to think there's probably something down at the base of physics that has to do with this idea of tension. And then I read your theory where you're talking about these little ether cubes being composed of a tension that's pulling inward, that's compressing at the same time that the quantum is pressing out and expanding, so that this pulling and pushing are happening at the same time. I thought it was just pretty interesting.
That's an interesting reference I hadn't heard before. Yeah.
Well, I can send you a page with all the translations on it of that word.
Okay.
Yeah, I might find it interesting. So you have the assumption that there is an objective reality. And why is that important to the theory of ether?
Well, that's a good question. It's basically it's the founding axiom for the entire
Mhm.
for my entire work is that there's an objective reality, and that's kind of that's a departure from the Einsteinian view, which was one of observational supremacy. And it's I guess founded on a belief, but the other aspect of it is that once we begin with that fundamental axiom and then draw up our hypotheses, we can still test. We can build our hypotheses up and test it. If you abandon reality, objective reality, I've never understood what people even mean. I mean, when you've got these entangled state experiments and these different interpretations of quantum mechanics, when people say anything about not having an objective reality, what do you replace it with? I mean, I think you replace it with nothing. I mean, to me, things do exist externally to me, and they exist externally to mathematics, and they exist externally to ideas. There's a real physical existence that we interact with all the time. And I think this is somewhat of an obvious thing to most people. But then the rebuttal has always been, well, physics doesn't have to be obvious, and maybe we're moving beyond it. But I never understood exactly what it is we're moving toward. Because to me, once you give that up, you don't have anything.
Well, certainly there are a lot of implications. And there's so many different, I mean, there's so many different theories out there about what it is if it's not objective reality. But my observation has been that most of the people that want to say that there is no objective reality are looking at the universe as really strictly particles. I guess that goes all the way back to Democritus, who said that everything is just atoms and the void. And that totally reductionist view that everything is particles. And as opposed to a view that everything has a whole, everything has a being to it, that a person is not just composed of particles. A person is a person with identity, and it's their identity can actually have an impact on their particles. The choices that you make can actually have an impact on the cells that make up your body. Equally well, the choices that your cells make have an impact on your body. So all the way down through all the levels, there are choices going on, and those choices are affecting the whole. But without the whole, there wouldn't be any identity for all the parts that are there. So if you want to imagine that a human being is just a bunch of quantum particles, and there are some theorists out there who say that the only reason we recognize objects is that evolution fitted us with a kind of an icon, a computer icon that allows us to recognize objects to keep us from dying, and that's the only reason that we see that, which seems to take all the meaning out of everything. So
Yeah.
I mean, there's a lot of different aspects to this, but I wonder what you think about this idea of the whole and the multiplicity, like the unity and the multiplicity of everything.
Yeah, I'm not a fan of I've dipped my toe into this on Twitter, and I took a lot of incoming flack, which was great because and my thoughts, I guess, are a little bit different from what you've described, and certainly considerably different from what what you just mentioned at the end from the atheistic community about things just being this a determinate result of evolution, and everything's just basically dead matter, that we're in some sense just deluding ourselves that we have any choices. But I don't go as far as to say that our cells necessarily have a choice. I've always been of the belief that there is a human soul that is at the level of the whole human, and that's where the choices can be made. Now, clearly other things do happen. Your heart beats without you trying to make a deliberate choice that it happens, and things of that nature throughout your body. But I don't I certainly don't subscribe to the pantheon. I think it's what is it it's panpsychism. Is that the thing where every atom has its own soul or its own consciousness and that sort of thing? My
Mm-hmm.
my own view is that we as individuals have a soul which is confined to our body during our lifetime, and that when we die, we're freed, that our soul is freed from our body, and I believe it's a separate existence, and that's a viewpoint that a lot of physicists scoff at. But my rebuttal to it is we don't do experiments on human subjects. So we're not scattering off of anything to try to find it. In fact, we exclude, for sure, we exclude people from twiddling the knobs when we're trying to make a measurement. We try to stop scientific fraud so they don't alter the pages of what they're producing. So we work very hard to keep any human soul activities out of our results. We have to, otherwise our results wouldn't be any good. But by the same token, that means that there is an inanimate world that doesn't have these choices to be made. the laws of physics are repeatable. It's been tried to do telekinetic effects by people concentrating to make an electron beam move. You're not going to be able to do that unless they can twiddle the knobs to change the magnetic fields. So to me, there's a separate physical world that clearly exists, and it's described well by physics. And then I believe there's a realm of the soul, which I believe allows choices. And I think at the end of the day, that it's the ability to make a choice that is what defines whether or not a person would have a soul. And you do get into a little bit of a fuzzy area when you try to discuss the difference between what's meant by a soul and what's meant by consciousness. Because I think in the atheistic scientific community, there's a fairly strong support for the idea that there's consciousness, but I believe they believe that that ends with the end of the physical being, and I don't believe that's true. And I've been trying to defend my beliefs, and it's somewhat humorous because it gets at some point you can't necessarily decide the issue. It's not something that has a ready answer. You can't readily go out and do an experiment. Although I did do one. I wrote it up about the experiment I did on my young sons. I shook up a box of pennies and I asked them to turn them all to heads. One of my sons asked to turn it to tails, but they got all 100 right. And if you calculate the odds of that happening, it didn't happen by chance. So there was something somewhere that was making a choice. And that's a very trivial example, but the odds of it are enormous. And then when you think about all of the decisions we make every day, every word I speak, every letter I type on the keypad, there's no way that that would happen in a random environment that just it ends up from evolution. There's too many choices that are being made. The odds of it happening are just enormous. So
I totally agree. Have you ever read any Dallas Willard?
no, unfortunately, I have to work for a living, and I spend my free time developing my theories. And I
Well,
mentioned to you earlier, I needed to get out
I'll
of my
send you
cave.
a relevant clip of Dallas Willard, but he was a wonderful philosopher, wonderful thinker, wonderful Christian. And he talks about the soul in a way that I've never heard anybody else talk about it before. Near as I can tell, he's kind of talking about it as being a kind of an organizing principle.
Okay. Well, I
And
look forward to looking through it.
yeah, in that sense, even a plant has a soul. If you're thinking about the soul as being a kind of organizing principle. I thought it was interesting that because a plant has to somehow organize its life. they they turn towards the sun, they receive the sun, they receive the water, they bring the water up both from the ground and from evaporation on the leaves, bringing the water up. So there's something that's organizing the life of a plant because they're very complicated. And then also their roots underneath the ground are sometimes some plants are actually helping other plants. Some plants will offload nutrients that they don't need, and then other plants that need those nutrients can gather them up. So there's this whole ecology going on that we don't know anything about mostly. But I was always taught early in my Christian walk that the soul is the mind, will, and emotions. So you have the body, then you have the soul, and then the spirit. So the soul is the mind, will, and emotions. And that would pretty much cover choice, wouldn't it? We choose with our mind, we choose with our will, we choose with our emotions. And some of those choices are wiser than others.
That is correct.
I like your idea that the soul is the chooser. I like that idea very much.
Yeah, that and memory. It can keep memory as well.
Well, would memory be part of mind, or is memory a separate thing?
Well, I mean, it's just my belief that the soul can keep memories as well. I
Mm-hmm.
mean, this is just purely speculative because we don't have, other than our own bodies, we don't have any interface to the soul. And like one of the things I've thought of is when you have Alzheimer's and that I believe that it's entirely possible that you lose the interface between your mind and your soul, but your soul may still keep the memories that you had. And it's a thought I have that might be what goes on. But when you get into that realm, when you can't really do the physical tests, it's pretty much speculation.
Well, it certainly is curious that, like, the body that I have today is not the same body that I had, was it 7 years? With every 7 years, every single cell in your body. I mean, some of your brain cells change out much faster than that, but your entire body has changed out all of its cells at least once every 7 years.
Hmm.
But still, all my memories are there. Even my muscle memory, even though those are not the same muscle cells that built in that muscle memory 20 years ago, I can still get on a bike and ride it today because of my muscle memory. And even though I'm not the same parts anymore, I still have all the same memories. I'm still the same person. I have the same identity. I've
Mhm.
certainly, there's parts of me that have grown and changed, but that's a very curious thing. And I think that's a very hard thing for the hardened materialists to explain. It's like the ship of Theseus.
Well, you don't have to explain anything if you're adamant enough about your assertions.
That's how you get away with it. You're just adamant. I enjoy your
Yeah,
Twitter feed very much because you don't let anybody get away with anything, but at the same time, you're very winsome in your replies and always very appreciative of people's participation. So,
thank you. Yeah, I try to be polite, and if you get a lot of incoming flack, it's noise. But sometimes people want to have discussions, and then that's when you can learn. I've been learning it. I've been learning from my feed too, because some people will send me, have you heard of this? And probably not. So then, dig into it and learn some more. So that's great.
well, and I appreciate so much you're spending the time with me because I know you have a day job and you're working on this theory. And one last question, I guess, you have put the paper out there. Have you gotten any feedback on it at all? Is it all flack, or have you gotten any positive feedback?
I haven't gotten too much feedback. I've had a few people start on it. The Ether paper is quite long, and so it's difficult to get through. I certainly get positive feedback on my on the Twitter feed still, and it's growing, so that's great. And for anybody who's watching, it's Larson Delbert is at Larson Delbert is the one is my feed on Twitter, and that's coming along. It's going to be difficult from my past experiences to be heard. There are a lot of people out in the community that come up with ideas that are clearly wrong, and they go. I've been called all those names. It's nuts, crackpots, lunatic, delusional, all of those things. And there are several papers that get produced in that are like that. And so when someone sees something, then you're an established physicist, because everything works in established physics almost. There's about five things or six that are pretty serious problems, which are addressed by this. But since everything else is working so good, there's a reticence for established physicists to step outside and deeply consider this alternative. So it's going to be a chore, and I really want to thank you because I haven't had an interview on it at all. This is the first one. So thank you for having me on your channel here today.
Well, I hope to be able to maybe I can move your theory up the food chain a little bit and get you some other interviews. I don't know. I'll try. I'll try.
Oh, that'd be great.
Yeah. This was just an absolute delight, Dr. Larson. I really appreciate you taking the time to talk to me today. And maybe if you have some time in the future, I'd love to have you back because I'd like to explore a little bit more some of your ideas about the soul. And you go quite deeply into that on your Twitter feed. So
Oh, yeah, thank you. This was great. Appreciated the time with you. It was nice to meet you, and
yeah,
great.
you have a great day. Bye-bye.
Bye.